Hello friends, I am Sridhar Chintala, Assistant Professor of Physics, ABV Degree College, Janagama. So in this video lecture, I am going to cover a topic from Modern Physics, BSc Maths 6th semester, photoelectric effect. So my talk is on photoelectric effect. So my talk goes like this. So photoelectric effect. So myself, Sridhar. So in this lecture, I would like to discuss about the history of photoelectric effect, photons, and photoelectric effect definition, and experimental setup to study photoelectric effect, and effect of intensity, frequency, potential on photoelectric current, and graphical representation of variation of photoelectric current, loss of photoelectric effect, and Einstein's photoelectric equation, verification of laws of photoelectric effect based on Einstein's photoelectric equation, and applications of photoelectric effect. So if you look into the background of the photoelectric effect, the phenomenon of photoelectric emission was discovered in 1887 by Heinrich Hertz during his electromagnetic wave experiments. In his experimental investigation on the production of electromagnetic waves by means of a spark discharge, Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by UV light from an arc lamp. Wilhelm Holwasch and Philip Leonard investigated the phenomena of photoelectric emission in detail during 1886-1902. Holwasch in 1888 undertook the study further and connected a negatively charged zinc plate to an electroscope. He observed that zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged while when it was irradiated by ultraviolet light. Positive charge on positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. From these observations, he concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Holwasch and Leonard also observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value called the threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. It was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light, having short wavelength to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium, and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons, and the phenomena is called photoelectric effect. In order to study the photoelectric effect in detail, we have to have a knowledge of photon, and we should able to know what is called a photon. After Max Planck quantum theory of radiation, there is a particle nature for light was observed, and that particle emits energy, and particle is called a photon. A packet or a bundle of energy called a photon. Energy of a photon is given by E is equals to h nu, and which is equals to hc by lambda, where nu is equals to c by lambda. And this h is the Planck's constant, nu is the frequency of the radiation or photon, and c is the speed of light, and lambda is the wavelength. And following are the properties of the photon. So if photon travels at a speed of light c in vacuum, that is 3 into 10 power 8 meter per second, and it has a zero rest mass, that means the photon cannot exist at rest. The kinetic mass of a photon is from E is equal to mc square, m is equals to E by c square, and where E we have hc by lambda. So hc by lambda by c square, the square and c cancel, and this is h by c lambda. The momentum of a photon is from E is equals to E square is equals to p square c square. We have p is equals to E by c is equals to h by lambda. So the momentum of photon p is equals to h by lambda. And these photons travel in a straight line. So the path of these photons follows a straight line. Energy of a photon depends upon frequency of the photon. So the energy of the photon does not change when photon travels from one medium to another medium. So upon moving from one medium to another medium, the frequency does not changes. That means the energy also does not change. The energy depends on frequency. So it doesn't depend on the medium in which it is traveling. And wavelength of a photon changes in different media. So velocity of a photon is different in different media. So wavelength of a photon changes in different media means the light travels with less speed in the denser medium, and the light travels with somewhat more speed in a rarer medium. So as the velocity is changing, the wavelength is also changes. Photons are electrically neutral, so they are having no charge. Photons may show diffraction under given conditions. Photons are not deviated by magnetic and electric fields, as it is neutral, so it is not deviated by magnetic or electrical fields. Then if you come to the definition of photoelectric effect, the phenomena of emission of electrons from mainly metal surfaces exposed to light energy. That light energy may be X-rays, gamma rays, UV rays, visible light, and even infrared rays of suitable frequency is known as photoelectric effect. So different types of materials will respond to different radiations. So there are different types of materials in our periodic table, right from alkali metals to the lanthanides and actinides. So the different types of materials respond to different kind of radiation. The electrons so emitted by this effect are called photoelectrons. The constituted by photoelectrons is known as photoelectric current. Some of the non-metals also show photoelectric effect. Liquids and gases also show this effect, but to a limited extent. So we are having three different figures here. So on the left hand side, we are having metals. So when they are irradiated by UV light, they are emitting photoelectrons. And the metals other than alkali metals, when they are irradiated by visible light, no photoelectrons emitted. And alkali metals, when they are irradiated by visible light, photoelectrons. So that means the different metals respond to different kind of radiation. So alkali metals are responding to visible light and the metals are responding to UV light. So different types of materials respond to different radiations. So upon the impingement of the light on the material surface, the material surface liberates electrons, and the liberation of electrons is known as photoelectric effect. And the liberated electrons are called photoelectrons. And the current constituted by these liberated electrons is called the photoelectric current. And not all the metals respond to all the different types of radiations. And even though the metals respond to a certain radiation, that light should have a minimum frequency. If the frequency is lower than that of the minimum frequency, the photoelectric effect is not observed. And that minimum frequency, we are calling it as the threshold frequency. So here we are having an experimental setup to study photoelectric effect. So in this experimental arrangement, we are having a cathode ray tube, a discharge tube. So in this electrical discharge tube, we are having a cathode and an anode, two plates, which are metallic plates, and we are having a window made with quartz, and this cathode is connected to highly negative potential, and the anode is connected to a positive potential with a rheostat. That means the potential of the anode may be varied. So from this window, when light is illuminated on cathode, this cathode emits electrons. So here we are using quartz window. Since the quartz is transparent to UV light, so we are using a quartz window here. So this is the experimental arrangement to study the photoelectric effect. So in this, we are having a voltmeter and an ammeter to measure the current, photoelectric current generated by photoelectrons, and voltmeter is to measure the potential between the cathode and anode. So in this figure, we are having C, the metallic cathode, and A, the metallic anode, W, the quartz window, and this is the photoelectron. So when light of a suitable frequency falls on the metal cathode, photoelectrons are emitted. These photoelectrons are attracted towards the positive anode, and hence photoelectric current is constituted. So in order to study in detail, we have to go step by step. So the above figure depicts a schematic view of arrangement used for the experimental study of photoelectric effect. It consists of an evacuated glass or quartz tube having a photosensitive plate C and the other metal plate A. Monochromatic light from the source S of sufficiently short wavelength passes through the window and falls on the photosensitive plate, that is emitter. A transparent quartz window is sealed onto the glass tube which permits ultraviolet radiation to pass through it and irradiate the photosensitive plate. The electrons are emitted by the plate C and are collected by the plate A by the electric field created by the battery. The battery maintains the potential difference between the plates C and A that can be varied. The polarity of the plates C and A can be reversed by a commutator. The commutator was not shown in the figure. Thus, the plate A can be maintained at a desired positive or negative potential with respect to emitter C. When the collector plate A is positive with respect to the emitter plate, the electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and the collector plates is measured by a voltmeter, whereas the resulting photocurrent flowing in the circuit is measured by a microammeter. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and the frequency of the incident light can be varied, as can be potential difference V between the emitter C and the collector A. So we can use the experimental arrangement to study the variation of photocurrent with the intensity of radiation, with the frequency of incident radiation, with the potential difference between the plates A and C, and the nature of the material of the plate C. Light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the emitter C. The intensity of light is varied by changing the distance of the light source from the emitter. So this is the variation of photoelectric current with the intensity of incident radiation and in the frequency of the incident radiation and the potential between the collector and emitter plate. So if you see here, this is the effect of intensity of incident light on photoelectric current. So on x-axis we are taking the intensity and y-axis we are plotted the current measured by an microammeter. And the graph between these two variables is a straight line. This indicates that if you goes on increasing the intensity of incident light, the current also increases. That means the current, the photoelectric current is directly proportional to the intensity of incident light. So as you increases the intensity of incident light, the photoelectric current also increases, and the relation between the intensity of incident light and current is linear. And next, the effect of potential on photoelectric current. So the potential between the anode and cathode, usually we call the potential of anode itself. So a graph is plotted between potential of anode in volts taking on x-axis and the ammeter, the current which is measured with an ammeter is taken on y-axis. And if you plot a graph between these two, the graph looks like this. So current initially starts to increase. Initially it is 0 when the potential is 0, and it starts increasing and increases with the potential of the anode and reaches a saturation value. So why this saturation is taking place? So for a fixed frequency and intensity of incident light, the photoelectric current increases with increasing positive potential applied to the anode. When all the photoelectrons reach the plate A, the current becomes maximum and is known as saturation current. For example, if the intensity is having some value, a fixed value, the photosensitive material liberates, for example, say uh, 20 number of electrons. So for a potential of anode, if 10 electrons are attracted towards the anode, and if you increase the potential of anode, more than 10 electrons are attracted, 12 electrons, 15 electrons, and 20 electrons. So if you increase the potential beyond this, there are no electrons to attract by the anode plate, so that the current becomes saturated. So when the potential increased beyond the saturation current, there is no change in the current value. And if you decrease the potential of the anode, current also decreases. When the potential is decreased, the current decreases, but not become zero at zero potential. So if you observe here, the current is not zero at the potential is zero. So that means it is not having a non-zero value. Even if the potential of the anode is zero, there exists some photoelectric current. So when the potential is decreased, the current decreases but not become zero at zero potential. This shows that even in the absence of an accelerating potential, a few electrons manage to reach the plate on their own due to their kinetic energy. So when the light is falling on the material, that light is utilized in two ways. One is to liberate from the metal surface, and the remaining energy of that photon is utilized in the form of kinetic energy. So as the electrons are having some kinetic energy, that kinetic energy is sufficient to reach the anode plate. That means even in the absence of the accelerating potential of the anode, a few electrons manage to reach the plate on their own due to their kinetic energy. So that is the reason we are having the photoelectric current even when the potential of the anode is zero. So when a negative potential is applied to the plate A with respect to C, photoelectric current becomes zero at a particular value of negative potential, is called stopping potential or cutoff potential. So what happens here is, it is not, the photoelectric current is not zero at the anode potential when we made anode potential is zero. So that means in order to stop the photoelectric current, we have to apply the negative potential to the anode. So when you are increasing the negative potential applied to the anode, at a certain value of the anode, the photoelectrons are repelled by the anode. That means no electrons are reaching the anode. So that means there is no photoelectric current. That means the photoelectric effect is stopped by the anode. So this potential of anode is called stopping potential or cutoff potential. And the intensity of incident light does not affect the stopping potential, and this stopping potential depends on the frequency of the incident light. Since the frequency of the photon is utilized in two ways, the after liberation of the electrons, the remaining energy of the photon is used in the form of kinetic energy of the electron. So the intensity of incident light does not affect this stopping potential, and this stopping potential is a direct function of frequency of the incident light. So effect of frequency of incident light on photoelectric current. For a fixed intensity of incident light, the photoelectric current does not depend on the frequency of the incident light, because the photoelectric current simply depends on the number of photoelectrons emitted, and in turn on the number of photons incident, and not on the energy of the photons. So if you increase the frequency of the incident light, what happens is photoelectric current does not increases, but the energy of energy of the emitted electron, the photoelectrons, increases. So that means the photoelectric current does not depend on the frequency of the incident light. So the frequency of incident light gives the sufficient energy to the photoelectrons. And the effect of frequency of incident light on stopping potential. So as we discussed earlier, the stopping potential depends on frequency only, not on intensity. So since the frequency gives the kinetic energy to the photoelectrons, in order to stop the photoelectrons, we need to apply a negative potential. So the amount of negative potential applied to anode is depends on the frequency of the incident radiation. For a fixed intensity of incident light, the photoelectric current increases and is saturated with increase in positive potential applied to anode. However, the saturation current is same for different frequencies of the incident light. So the saturation current means the number of electrons reached the anode plate. So as the intensity is fixed, the number of photons incidenting per unit area is fixed. So the number of electrons liberated by the incident light also fixed. That means the saturation current is same for different frequencies. We may have a potential is different for different frequencies. The negative potential applied to the anode is different for different frequencies. However, the saturation current is same for different frequencies of the incident lights. When the potential is decreased, taken below zero, photoelectric current decreases to zero, but at different stopping potentials for different frequencies. When the potential is decreased, taken below zero, photoelectric current decreases to zero, but at different stopping potentials for different frequencies. So as we already discussed, the frequency of the photon gives the kinetic energy to the electrons. So if we increase the frequency, what happens? The kinetic energy of the electron increases. So in order to stop the more kinetic energy particles, we have to apply more negative potential. So that is the reason we are having two different stopping potentials for two different frequencies. So this is nu 1 and this is for nu 2, and the stopping potential is V S1 and this is Vs2. V stands for potential and S stands for stopping. So Vs for nu 1, Vs for nu 2. So the variation of stopping potential with the frequency is as shown in the graph. So higher the frequency, higher the stopping potential. So the stopping potential is directly proportional to frequency. And if you plot a graph between the frequency of the incident light and the stopping potential, so the graph between, so in the earlier picture, we plotted a graph between the photoelectric current and the potential. And in this slide, we are plotting a graph between the stopping potential and the frequency. So the graph between the stopping potential and frequency does not pass through the origin. It shows that there is a minimum value of frequency called threshold frequency, below which photoelectric emission is not possible, however high the intensity of the incident light may be. It depends on the nature of the metal emitting photoelectrons. So if you observe the graph here, so this is the origin. So we have taken the frequency on x-axis and the stopping potential on y-axis. So if you increase the frequency of the incident light, the stopping potential also increases. But when you decrease the frequency of the incident light, the stopping potential also decreases, but the stopping potential becomes zero even when the frequency is not zero. That means the frequency should have some minimum value below which the photoelectric emission does not take place. And that minimum value, we are naming it as the threshold frequency. So this is the experimental observation of photoelectric effect. And these observations may be concluded in the form of laws, and these laws are called the laws of photoelectric emission. So for a given substance, there is a minimum value of frequency of incident light called threshold frequency, below which no photoelectric emission is possible, howsoever the intensity of incident light may be. Okay. So this is one first law, that is this gives the value of threshold frequency. And the second one is the number of photoelectrons emitted per second, that is the photoelectric current, is directly proportional to the intensity of incident light, provided the frequency is above the threshold frequency. So number of photoelectrons emitted per second is nothing but the photoelectric current is directly proportional to intensity of incident light. So this was the first observation, and this is called second law. And the third one is the maximum kinetic energy of the photoelectrons is directly proportional to the frequency, provided the frequency is above the threshold frequency. So we already know the kinetic energy is directly proportional to frequency. If you increase the frequency, the kinetic energy of the electrons increases. So the maximum kinetic energy of the photoelectrons is independent of intensity of incident light. And the process of photoelectric emission is instantaneous. As soon as the photon of suitable frequency falls on the substance, it emits photoelectrons. And this photoelectric emission is 1-to-1, that is, for every photon of suitable frequency, one electron is emitted. And next we are moving on to the Einstein's photoelectric equation. So in order to explain the photoelectric effect experimentally, so Einstein formulated an equation called Einstein's photoelectric equation. So when a photon of energy h nu falls on a metal surface, the energy of the photon is absorbed by the electron and is used in two ways. As I already discussed earlier, a part of energy is used to overcome the surface barrier and come out of the metal surface. This part of the energy is called a work function. Phi is equals to h nu naught. The remaining part of the energy is used in giving a velocity to the emitted photoelectron. This is equal to the maximum kinetic energy of the photoelectrons, half mv square maximum, where m is the mass of the photoelectron. And according to the law of conservation of energy, the energy neither created nor destroyed. So the energy of the photon is equal to the work function plus the kinetic energy. So the work function is h nu naught plus half m maximum square, mv square maximum. So half mv maximum square is equals to h nu minus h nu naught. So this is the metal surface. Photon is instanting on the metal surface and electron is liberated. So part of the energy of the photon is utilized as a work function, and the part of it is used in the kinetic energy of the electron. So the above equation is known as Einstein's photoelectric equation. According to this equation, maximum kinetic energy depends linearly on frequency nu, and it is independent of incident radiation. In agreement with the observation, this has happened because in Einstein's picture, the photoelectric effect arises from the absorption of a single quantum of radiation by a single electron. So the intensity of radiation, that is proportional to the number of energy quanta per unit area per unit time, is irrelevant to this basic process. Since maximum kinetic energy must be non-negative, the K maximum is equal to h nu minus h nu naught implies that the photoelectric emission is possible only when h nu is greater than the work function. That means the energy of the photon is greater than work function, then only the photoelectric emission takes place. That means nu is greater than nu naught. So the greater the number of energy quanta available, the greater is the number of electrons absorbing the energy quanta, and greater, therefore, the number of electrons coming out of the metal for nu greater than nu naught. This explains why for nu greater than nu naught, photoelectric current is proportional to intensity. So in Einstein's picture, the basic elementary process involved in photoelectric effect is the absorption of light quantum by an electron. This process is instantaneous. So whatever may be the intensity, the number of quanta of radiation per unit area per unit time, photoelectric emission is instantaneous. Low intensity does not mean a delay in emission, since the basic elementary process is the same. So if the intensity is low, even though intensity is low, the electron liberates instantaneously. Intensity only determines how many electrons are able to participate in the elementary process. So, and therefore the photoelectric current. So using K maximum is equal to E V naught, we can write E V naught is equal to h nu minus phi for nu greater than nu naught. That means if the frequency is greater than threshold frequency, we can write for the stopping potential as V naught is equal to h by E into nu minus phi by E. That means when you plot a graph between V naught and nu, you will get a straight line, and the slope of that straight line will be equal to h by E. This is from the Einstein's photoelectric equation. So this is the graph showing the variation between the stopping potential and the frequency. So during 1906 and 1916, Millikan performed a series of experiments on photoelectric effect aimed at disproving the Einstein's photoelectric equation. And he measured the slope of this straight line obtained from sodium, similar to that shown in the figure, using the known value of E and H, determined the value of Planck's constant H. This value was close to the value of Planck's constant determined in an entirely different context. And in this way, in 1916, Millikan proved the validity of Einstein's photoelectric effect instead of disproving it. So these are the applications of photoelectric effect. So photoelectric effect may be used in automatic fire alarm and automatic burglar alarm, scanners in television transmission, reproduction of sound in cinema film, in paper industry to measure the thickness of paper, to locate flaws or holes in the finished goods, in astronomy to determine the opacity of solids and liquids, automatic switching of street lights, to control the temperature of furnace, photometry, beauty meter, light meters, photoelectric sorting, counting, and metrology. So these are the applications of photoelectric cell, and this is the conclusion of my lecture. And in this lecture, we discussed mainly about the history and background of photoelectric effect, definition of photoelectric effect, and properties of photon, and experimental arrangement of photoelectric effect, and the laws of photoelectric effect, and the Einstein's photoelectric equation to verify the laws of photoelectric effect, and the applications of photoelectric effect. So this is the conclusion of my lecture. Thank you.